So, yeah, thanks for being here after the lunch break. I think some are still coming in slowly. I start anyway, not to delay everything. So some of you will have seen parts of this talk in a slightly incoherent version over the lectures last week because I distributed some of these slides into the other talk. So this time it will all be about levitated cavity-optomechanics and in particular about our efforts to realize that. And what I want to start with is optical tweezers. Again, some of you have seen this movie before. So it's a great tool. With optical tweezers you can do stuff like this. So this is 46 microspheres in liquid, which are controlled by light fields, and one can play Tetris or do all kinds of neat things. The recent efforts to go already one step too far, the recent efforts to levitate particles, of course, can rely on this kind of technology to some extent, but then at the same time, in liquid, all of this is highly overdamped, and that means that you would not so quickly start to do quantum experiments in such an environment, right? It's hot, it's strongly interacting with the bath, and so on. And then there have been some more serious experiments, and I like to pick out two that I particularly like in these liquids. For example, here people analyzed how a certain motor protein walks along some strings inside the cells in the body, and they know now that this little thing is limping because they did precise force measurements on this big microsphere that it's attached to, or in other respects, more in the direction of statistical physics. People have been analyzing the phase landscape of DNA, how it folds. So the free energy landscape of a DNA, how it folds, also by precise force measurements on such particles. And all of this was born in the 70s with Arthur Ashkin's work on trapping particles. And he did that also first in liquid, and out of this biology branch, a lot of science developed. But then he also did experiments where he levitated particles. And here this would be 10 to the 20 micrometer sized silica spheres or silicon oil droplets, which he actually managed to hold with radiation pressure against such a green laser beam. And then they would be trapped in this vacuum. And if he had at the time already been able to stabilize that so much and looked at the mechanical qualities of this, then he would have been very well able to compete with any mechanical resonator that we have today, as we will see in a moment. And in this optical trapping, of course, another very important field, and this is probably the most important one for us, has developed by this idea that you can use light in the same way to trap atoms. This is from the first experiments where a neutral atom cloud was trapped in a purely dipole trap. And yeah, so this work in the 80s started together with some other groups. Of course, the whole quantum optics and manipulation of single particles, which also recently won the Nobel Prize. So now, when we look at this, so here are the more like a sketch of one of the more recent atom experiments where one can nowadays control the system as a two-level system and do all kinds of nice cavity QED. And then when one looks at bigger sizes, then there's all that has been covered in this morning's talk by Markus Arndt on matter wave interferometry. And on the other side, as many of you heard last week, there is for a very big mass range, there's Cavity-Optomechanics, where one tries to do quantum operations on really, really massive objects, speaking of 10 to the 14 to 20 to the 20 atomic mass units or so. And in between here lie these nano and microparticles in size. And it's somehow an interesting size range because the polarizability of these dielectrics is already so big that one can hold them in optical traps. So one has essentially a mechanical oscillator, like the clamped oscillators one looks at in Cavity-Optomechanics. At the same time, if they are optically trapped, we can do a type of experiment that is done with the molecules, namely matter-wave interferometry. So this is one of the major motivations, and also the one that makes this to this conference, I would say, for people to study this kind of system. Now, talking a little bit about this one here, over the last 6 years, Cavity-Optomechanics has really gone into the quantum regime, and there have been many, many nice experiments, and I will not talk about all of them, of course, but just go quickly through the ideas and give an idea why this type of control that we have here would really be something useful when it goes to manipulating the nanoparticles, eventually also for matter-wave interferometry. So, in essentially all Cavity-Optomechanical systems, what one needs is, this is the paradigm, right? One has a Fabry-Perot cavity, and one of the mirrors is movable, typically a harmonic oscillator, and what one needs is the interaction between the light field and the mechanical motion, and this interaction one gets because the resonance frequency of the cavity is changed when the position of this mirror is changed, obviously. And then to first order, we have this term here, and that would give rise to some coupling. And there's many, many ways how this has been realized. So that's the Fabry-Perot cavity, but then there's also whispering gallery modes in such a vibrating toroid. There could be membrane in the middle approaches where such a membrane is sitting on the slope of the intensity field. Equal dispersive physics would be when there's atoms sitting here, which gives also rise to a nice optomechanical system, or the nanoparticle. This here is a microwave capacitively coupled oscillator, so there would be a microwave cavity and this membrane, which is capacitively coupled to that. Or I've been talking about all of this a little more last week, these kind of photonic crystals, where one has very high frequency and extremely high coupling to the light. And just to, not randomly, but there's many other experiments, as I pointed out, so I picked out 3 that kind of show how it was going. So first, laser cooling in optomechanics was this, and actually also a paper by the Teufel Group and Lehnert in 2011. And then in this group, Lehnert and Teufel et al., they have actually managed then in 2013 to do entanglement between the microwave field and the mechanical resonator. So we're here really talking already very non-classical. And a recent experiment in the Aspelmeyer Group was actually to really now use single photon excitation with a single phonon excitation in the optomechanical crystal to see non-classical correlations between them. And that is eventually going towards seeing entanglement as well, which is not possible at this point due to high losses. But so this and several other things show, for example, where people did squeeze state of mechanical oscillator, show that this system works now in the quantum machine. And it's usually governed by a toolbox of things we can use. So by detuning the driving of this optical cavity, from the resonance of the cavity, one can, in the resolved sideband regime, where the frequency of the mechanical oscillator would be higher than the line width of the cavity. In that regime, one can, by detuning the laser that drives the cavity, go to different interactions. So one can achieve a beam splitter interaction between photons and phonons. One can achieve a two-mode squeezer interaction, which has actually been used in this entanglement experiment. And if one goes on resonance, one essentially has a XX coupling, which gives rise to a quantum demolition readout, which is then in the end the way to actually, one way to actually go towards squeeze. And of course, one has to fulfill several conditions to do that, to do this kind of things well. And in the end, it boils down to what is called the cooperativity. There's sometimes a 4 here, where the coupling between the light and the mechanics squared over the loss rates, which would essentially be the loss from the cavity, and the loss to the phonon bath needs to be larger than 1. And so that would be the strong cooperativity. But then if you want to do something meaningful and see the quantum effects, you should also start with a state that is pretty pure. And if you then want to go, so that all would give you linear interactions. And if you then would like to do something nonlinear, then you would have to rely on using the photonic states for that. Say one has an entangled state and does a kind of projection, or what people did in quantum optics as photon subtraction or simulation. And so all of these regimes have been achieved. Some of the experiments I mentioned already. All of the regimes have been achieved, and now one actually has in different systems, different parts of the toolbox available. If we rewrite this cooperativity a little bit differently, then we get this inequality, which essentially here you see that would be the rate at which, so it's just the coupling square over the cavity decay, and that should exceed something that goes both with the temperature and the mechanical quality of the system. And of course, this is one of the essential things that people have been working on to increase the mechanical quality of the mechanical resonators. And here is a plot for all kinds of systems, not only optomechanical systems, that shows that one can observe, without really giving an explanation, that one can see that the length scale at which the resonator is somehow scales with the mechanical quality. So larger scale oscillators typically have a better quality factor. Now, I've been talking about this idea of optical levitation to get a better mechanical quality, and even though it's pretty young, right? This optical levitation for this kind of purpose has only started like 6 years ago or 7. The points that we find for levitation are really up here, quite above this line. And this is what I've been talking about, the Ashkin experiments. If he had been showing the mechanical quality, then it would have been here, roughly. And for the systems that are currently in use, here, for example, that is the group of Ramanujan and Lucas Novotny. They have this tweezer with a little nanoparticle, and they are holding currently the record in cooling that via feedback cooling with, as far as I know, they can now go down to 20 phonons of occupation in the mechanical resonator. Then there is an experiment that also uses 3D feedback cooling by Hendrik and co-workers in here, and then one should also mention in the whole context that meanwhile in 2016 also a clamped system has been fabricated that actually lies in a comparable range with a Q of 10 to the 8 and the frequency of I think roughly a megahertz. So somehow I mixed up things, so I should mention there's also a second paper by the Senki group, which has done essentially the same quality and the same design, also at the same time. So as you can see, the mechanical quality of these resonators by levitation is really good, and so we're hoping that this is a good starting point for optomechanical control. Now, it has also been shown now that at this point, this is exactly where they are right now, this blue point. At this point, one starts to not be limited anymore in damping by the surrounding gas, but suddenly the recoil from the trap photons is what is heating the particle most. So these are nanoparticles which are cooled down to roughly 60 phonons, and then the cooling is switched off, and one can look at the heating up of these particles, and what they see is consistent with what one would expect for recoil scattering. And this is something that is highly related to what people have also recently observed with mechanical membranes and they say standard optomechanics, where suddenly measurement back action becomes relevant. So the noise induced by radiation pressure would actually dominate the measurement compared to the damping from the environment. And a nice thing that one can easily remember in this context is that when you think that all the gas is gone and you just limited by this recoil scattering, then this essentially acts also as a bath that induces Brownian motion, which due to Doppler shift induces some damping and of course heating because of this recoil. And this bath would equilibrate at h bar omega. So that's essentially the temperature that the nanoparticle sees if it just has the light field. Of course, this is very weakly coupled, and the mechanical quality, depending on your trap, could still be 10 to the 10 or 10 to the 11. Now, this is another, in the comparison of levitated versus clamped optomechanics, the mechanical quality is not the only thing. This is a little demonstration that shows that there's another little advantage. When you look at the green, that is that's a spectrum of the whole set of mechanical modes one can see, and the green is a spectrum of mechanical modes in the silicon nitride membrane, and the red is the spectrum one can see for a levitated nanoparticle. In the end, the levitated nanoparticle really has, as long as it's in the linear regime, really only these center of mass motion degrees of freedom, and if it's not a completely symmetric trap, then one would have 3 frequencies. And this is very nice, especially if one wants to work in the time domain. Then, I mean, in the frequency domain, I can integrate over a long time. I can always pick up one of these very narrow keys. But if I work in the time domain, I cannot do this, right? I need to find some way how to get rid of all these other So that was some motivation for using levitated mechanical oscillators, and really the idea that was published in these papers in 2010 was to do essentially Cavity-Optomechanics with this. And Oriol Romero Isard, who is one of the authors of the 3 papers, he actually also directly discussed this option for doing kind of matter wave interferometry by not only cooling this particle, but really by letting it loose and having a kind of matter wave interferometry experiments. As we heard this morning, for this kind of masses, so we're talking here, I think 10 to the 14 atomic mass units, no, 10 to the 11 atomic mass units. This is for 100 nanometer particle. This is really, really a hard thing to do, and we're essentially, phrasing it in other words, working on a source for that. Right? How the matter wave interferometry would be done is the next question. And and this was one of the proposals at the time, where the particle would be cooled up here, and then it falls down, and this part here that you saw would be a projective measurement on a double slit. So that would be one optomechanical way how to prepare probabilistically a superposition state as an alternative, if you like, to really using a grating. But then, of course, when with all the numbers done, this is, sorry, doesn't work. But this is really hard. So in order to do this without decohering the state, one needs a super high coupling between the particle and the cavity, which essentially means that we need a cavity with a very high finesse and that is very short. And then there's also all the other numbers one has to look out. It's terribly hard this way, and maybe not the way that people would do it, but it shows that we can use the tools of optomechanics not only to do the cooling, but also to do something for state preparation. And of course, for the cooling, you also don't need to have a cavity. I mean, as I mentioned already, the feedback cooling experiments by Lukas Novotny's group, and also Hendrik has proposed that one can do feedback cooling, and actually with the levels one can reach in the experiment do meaningful matter wave interferometry. So one could ask, do we really need to bother with cavities? And as I'm doing that, I obviously would say yes. So what the cavity can give us, in addition to just cooling, is all the tools that I showed you with the optomechanics. So there's protocols for transfer of a single photon onto the mechanical oscillator. There's protocols for state teleportation, where one could kind of do projective measurements on the light field to get a certain mechanical state. And there's reservoir engineering techniques which can actually give you squeezed states of mechanical motion. To my knowledge, there's not too much work out so far on going towards testing alternative theories or doing matter wave interferometry with states that have been prepared directly optomechanically in such a cavity and then dropped. So there's still nice ideas to be found. But the principal idea, I think, is clear. One can prepare quantum states, and one wouldn't have to bother about the grating. And then there's, of course, also other possibilities. In contrast to clamped oscillators, one can modulate the mechanical frequency of the oscillator very easily via the second light field. And this is where something that I'm personally very interested in comes in. This gives essentially control over both temperature and energy landscape of this particle, and allows one to do statistical physics experiments in the end. So if I have time in the end, I will still talk a bit about this. So experimentally, cavity cooling has been done in several systems. One of these systems is ours that I'm going to talk about briefly, but also you heard Markus Arndt mention the experiments where the particles actually in vacuum fly through the cavity and are cooled in transition. As we heard, they can also now trap them. There's the group by Peter Barker, which actually have a combination of optical and ion trap, essentially, to hold the particles, which solves a problem that we always had, namely when one has a particle to go to very low vacuum. It's not so easy as it turned out, and with the ion trap one can do that. So, and then there's also the group by Ramanujan, which have recently been showing that they can trap a particle in a kind of tweezer and then move that into optical cavity. They're now working on showing the cooling of that as well. So very briefly, as time goes as always quicker than I thought. So this is our experiment. What one needs to do, one cannot just have the particle in a cavity. It needs to be trapped and it needs to be coupled to a light field. And because it's not coupled when it's in an intensity maximum, one needs a second light field that is phase shifted. And we do this by having two light fields in the cavity that are shifted by 1/3 spectral range, which means there's one node missing, so to say. And at a quarter of the cavity length, one gets this kind of configuration where the particle is trapped in both fields but moves along the slope of one of the two light fields. And as the optomechanical coupling goes with the slope of the intensity distribution, this results in some coupling. I won't go through the details of the setup. Only here a little picture of the nanoparticles under the electron microscope. We use this medical nebulizer to spray them into a vacuum chamber, which is of course not what you want to do forever if you want to work at 10 to the minus 10 millibar later on. So we're going to change that, as you will see. And then when we have the particle in there via heterodyne detection, we can read the spectrum of the particle. So I'm going to accelerate for a few slides simply because of the time. So we can show that this is really a nice optical trap. And then the next step would be that we want to show cooling. And this sideband cooling is really something that people have done studied in optomechanics, and actually it's the same as with ions. When we detune the light field, the middle peak here would be the laser drive, and this is the cavity envelope. If that is red detuned, then one has an enhanced scattering into higher energy modes, and that is actually where the mechanical resonator loses energy. And on the other side, where one scatters into lower energies, there one would heat the particle. And we could show, that was in 2013, how an increase of the cooling laser would change the optomechanical coupling, and how that would actually lead to cooling of the mechanical motion. And the cooling here is to 50 Kelvin, and this is because this particle is pretty much dense. A guitar string has a higher Q than our mechanical resonator at the time had. And the reason for that was that we were pressure limited due to what I mentioned, that we would lose the particle. But what we could infer from that already was that the cooling rate we have would actually serve to go to the ground state at 10 to the minus 7 millibar. And this plot briefly shows what the parameter regimes are. So we want to have the cooperativity larger than 1. The heating rate here could come either from the thermal environment or from the recoil heating. That depends on the regime. So, under the blue line, one would have the whole thing dominated by recoil scattering. This is independent of the size of the sphere. And under the red line, the cooling one can achieve is actually larger than the thermal heating rate. So when we look at the size of particles we had, then one can see that we are scattering recoil limited at 10 to the minus 6 millibar or so, and that at this point the cooling rate is also sufficient. And if one changes the particle size, then one doesn't get much of an effect if one is in this regime, because the intensity of the laser goes both in the coupling and in the recoil heating, and they just cancel out. So it's all, in the end, just a property of the cavity, how strong this cooperativity is. So the solution to the problem is going into an optical tweezer where people actually can go to very low pressures. And in our lab, we now reach 10 to the minus 7 millibar with a feedback cooled particle. So that should actually be fine. It's a 70 nanometer particle, so we are on this blue line, so that should be fine. And now we really have to combine the setups, and this slide is a bit technical, so we have set that up. We get cut mirrors, and such that the numerical aperture of the tweezer can be high, it's 0.8, and then we can hold a particle with this tweezer into this optical cavity. here's a sketch of the cavity mirrors. And of course, this is very similar to the approach that the Kiesel group follows, moving a particle to the tweezer inside. Now we had a problem that was that loading in this tweezer works well if we use a high density solution of particles, and loading into the cavity works well when we use a low density solution of particles. If we switch the whole thing around, we either don't trap in the tweezer or we make our cavity mirrors bad. So that's how it works currently. Here's the tweezer, here's a trapped particle, and let's see if it works. And so once we have the particle trapped, we would take the cavity with our hands and then move it around the particle and then close the vacuum chamber and then pump down. So that works, surprisingly. We were very happy to see that. I mean, it means that the particle has to stay while you align the cavity and while you make everything working and so on, while you pump down to 10 to the minus 7. It's not nice. But we hope to show first experiments with that. But this is really the solution that we want to go for. It's a hollow core fiber that would really deliver our particles from some high vacuum environment to the low vacuum environment. And then we hope that we can put the particle out of this hollow core fiber and put it into the cavity mode or into the tweezer mode. And this is the state of affairs in this context. So the idea is that we do very similar to the conveyor belt experiments for atoms in the Mesoscopic group. We would have a conveyor belt for the nanoparticles, 2 light beams focused into a hollow core fiber. That's a hollow core photonic crystal fiber, where here is a 10 micrometer hole that can guide a single mode of light, a bit more than only a single mode. And we would trap the particles here and then guide them inside. And some experiments in this direction have already been done by the group of Philip Russell, who was one of the people who can make the fibers himself and so on. What they usually looked at is micron particles. We now need something around 100 nanometers. Yeah, so this is the setup because it grew bigger than we planned it. Here's the fiber between 2 test chambers. So we have already combined it once with the cavity, but that didn't work out so well. So this is what the data is made with that I will talk about. And these movies don't really work well. So, and if one then detunes one of the 2 light fields, one gets one then detunes one of the 2 light fields, one gets this moving conveyor belt, and with a 10 kilohertz detuning, one would see the particle here go with a few centimeters per second. Just forth and back. So that works nice at high pressure. Low pressure is something we also need to solve, and this is why we've been working on some feedback cooling. Also, I will show you in a moment. But this is first a little bit of an analysis of this optical trap that one gets here. So when one can very precisely move this particle by just starting the conveyor belt and stopping it again after a very short time. And then one gets this kind of frequency dependence on position inside the fiber. And the more careful analysis shows then that the hollow core fiber can also guide higher order modes, light modes. And these higher order modes lead to some kind of trap that looks rather like this. Red is where the trap is really deep. And so the particle would move along here and have a high frequency here and a lower frequency there. And that's why one sees these wiggles. Then when the particle is moved out of the fiber, then one sees that the light beam spreads out, and that's why the frequency of the particle would go down axially, because the intensity just gets lower. And this is nicely shows that we can move the particle out of the fiber and actually far enough to move it into a cavity. So in principle that should work. The only problem to solve is how does one actually move this one end of the fiber with the 2 coupled light fields into the cavity. And by adding yet another laser beam here, a green laser that is focused into this hollow core fiber, one can exert some radiation pressure on the particle, and because we can read out the motion of the particle in 3D, we can actually apply feedback cooling. So we just, whenever the particle goes towards the laser, we turn it on, and whenever it goes away, we crank it down. And this way the particle sees some velocity-dependent force, and that's damping. And if one, with averaging over many particle traces, one can actually introduce this damping, then we start at some energy of the particle. This is normalized to thermal equilibrium. If we switch this on, then the energy of the particle would decay, and we can keep the feedback cooling on. And once the feedback cooling is switched off, we get some kind of artifact which is not related to the particle, and then it goes back to thermal equilibrium. And this is also a nice tool because our intensity of the laser is not 100% stable, which means that at low pressures where the line width is really narrow, we cannot easily measure the damping of the motion of the particle by looking just at the width of the mechanical spectrum. So the time scale at which this thermalization happens here is actually another measure of how strongly the particle is damped by the environment. And so that helped us to answer a question that had been around for a while, namely, if I want to do this really with a high pressure on this side and a low pressure on this side, and then I want to move my particle along here, where is what pressure? I mean, this sounds like a simple problem, right? One just has to look into the literature and look for the equations, and then it turns out that's really long papers with really ugly equations. So we measured it, and it turns out, this is a log-log scale, that's why it looks so bent, but it turns out the dependence is actually linear. So this is not consistent with some things that we read at the time. There's not many measurements existing, and they typically inferred the pressure distribution from the flow. So that was kind of a side project, or is still a side project to the whole towards quantum stuff that we are actually with the group of John Zader looking at what we would expect. And they did some Monte Carlo simulation of the full nonlinear Boltzmann equation, and they see that so this was after a week of simulation, so that was still continuing then, but I don't have any data. So they see that they would also see this linear dependence. And then the question was how comes that other people see nonlinear dependencies? As it turns out, it's really, as one would expect, it really critically depends on the pressure regime one is in. Here we are already seeing essentially a diffusion process where each of the atoms is diffusing along the fiber like randomly without interacting with the other gas particles so much. But if the pressure on this side is much higher, then one actually starts to see a nonlinear behavior of the whole thing. This is something we can measure and compare to the simulations and also to analytical results that this community has. And they are very happy because pressure sensors for capillaries don't really exist. And there's some ideas that people use, but this is a very precise pressure measurement. So I have 1 minute 30 left. So I use my 1 minute 30 to quickly talk about something. So something else. So what I showed you so far was really our way towards having such a nanoparticle, somehow quantum controlled, and then do things that might test just superposition states of microscopic objects. Another nice thing that one can do with these nanoparticles is look at thermodynamics, and I sketched that in a minute. So you know this Stirling engine, and the Stirling cycle is one where you can, if you do it infinitely slow, really do work at Carnot efficiency with. So one would change the pressure and the volume and on such a cycle and can gain energy from the system. People have looked at that in a kind of a single particle analogon. So the volume would correspond to a width of a harmonic trap, and the pressure would correspond to the volume, and the temperature would be a surrounding temperature, and our system is just a single particle in this trap. So you can imagine that the probability distribution of this particle in the trap corresponds, so to say, to the gas. When I make the trap narrow, I would compress the gas. And that has been analyzed in liquid, and there has been even an experiment. And one can show what are exactly the times, the protocols at which, how fast do I have to change my temperature, my trap stiffness here, how fast do I have to change my temperature here, that's actually instantaneous, in order to get the maximum efficiency. But, the question one can answer by that is, if I don't do it infinitely slow, but I really want to get power out of the system, then I need to do it faster, and I obviously lose efficiency, and that's the best efficiency one can get in this kind of system. And one can look at the underdamped analogon of this. This requires some new analysis, and I've been working with Erik Lutz and Andreas Dechand on it. And in a nutshell, Andreas could show what the optimal protocols in the underdamped regime are. This is what you would see here, how one changes the frequency, and one needs to do a step in frequency and then go up again. So it's exponential protocols, and these steps are actually an artifact that one gets in the underdamped regime that have been predicted but not measured so far. And we have shown that exactly the experiments that I showed you actually can help via cavity cooling and via changing the trap stiffness to implement this kind of program. And so this would be one example of where one can do statistical physics with these little nanoparticles. And the idea is, of course, maybe first look at this regime where the stochastic thermodynamics is actually not worked out completely, and no experiments have been done essentially on this. But then really go to the quantum regime, which I said in the beginning, in liquid we cannot possibly do. What happens if radiation pressure, if shot noise is the thing driving my particle? Can I overcome it? That would reduce my efficiency. Can I overcome that by using a reservoir that is actually squeezed, like a non-thermal bath? This would not have to follow the Carnot efficiency anymore, because that's only made for thermal baths. So, and in the end, can I build a quantum heat engine? And that would be just one of the many questions one could ask when such a nanoparticle is in the quantum regime from a thermodynamics perspective. I won't have time to talk about that anymore. MAQRO has been mentioned at several points throughout these days. So I thank you for your attention.
Thank you very much for your nice talk. Any question? Let's thanks again